Hey, welcome back to Calculus. In this video lecture, we're going to take a look at some problems in section 11.11, which is about applications of Taylor series. There's more material in this section than what I'm going to present here in this one video, which hopefully won't be too long. And although we're not covering any new material next week, we still have 4 more class meetings where we can discuss these and other applications of Taylor series. We'll just do it more in the form of office hour chats rather than me preparing new material. Okay, so you can see the outline of the lecture there. We'll just get started. I want to tell you, and you already know what I mean by this, but I want to make a kind of formal definition of what I mean by a Taylor polynomial. I mean a partial sum of a Taylor series. And then I want to show you some math problems you can do with Taylor polynomials, approximate solutions to problems, calculate some limits, and so on. So that's the whole spirit of this business. If you're wondering, like, why did I live through chapter 11 to get to section 11.10 so that I can work with Taylor series? Well, it's because if you cut a Taylor series off somewhere, you have a polynomial. And a polynomial is mathematically kind of easy to work with, differential and integral calculus wise. And if that polynomial closely approximates your function, then that's good enough for practical purposes. All right. When we make approximations have error, and it's very important always to be able to understand and control your error. We won't delve into it quite as much as we would in an ordinary semester. We would have worked a little bit more on something called Taylor's inequality, but I'm at least going to state it for you and give you some idea of how you can control the error. Because making approximations without having any control or sense of how big your error in your approximation is, it's kind of an irresponsible thing to do, and I don't want to pass irresponsible habits on to you. Okay, but let's just get going here. So we'll start with something familiar. You know what I mean by the Taylor series for a function centered at A. I mean this infinite series. This infinite series expanded in powers of x minus a. And the coefficients are those nth derivatives at the center divided by n factorial. And if you write that thing out, when n is 0, remember 0 factorial is 1. So the 0th term of the series is just f of a. The 0th derivative of a function is just the function. And then you let n equal 1, you get the first derivative at a times x minus a to the 1. Again, 1 factorial is 1. And then f second derivative over 2 factorial, and so on and so on and so on. So nth partial sums of that series are called the nth degree Taylor polynomial. It's nth degree because if you take the counter out to n, then the exponent that you're going to stop, you take a partial sum, it'll be nth, so you get an nth degree polynomial. So I can show you here just with the laser pointer. If you just took this first partial sum, I would write that as t sub 0 of x. T sub 0 of x is just a constant. T sub 1 of x is the partial sum that contains where you take n out equal to 1. So I'm underlining it, and I'm actually going to highlight t sub 1 of x. Yeah, yellow is good enough for me. Let's make it a little whiter. Maybe you recognize what t sub 1 of x is. If you just take that part of that polynomial, let me write its name down here, the first degree Taylor polynomial. You recognize that? It's f of a plus f prime of a times x minus a. The first degree Taylor polynomial is just the tangent line. Maybe you've been seeing that in the pictures I've been drawing with Desmos, that when we ever clicked out that counter to 1, that's just the tangent line. The first degree Taylor polynomial is a linear function that closely approximates your function at the center. That's what the tangent line does. So in that sense, if you want, T2, I don't know how to highlight it without making the slide all ugly, but T2 would be the second degree Taylor polynomial. If you want, you could kind of call that the tangent parabola. T3 is the tangent cubic. T4 is the tangent to the 5th degree. It's and so on and so on and so on. So that's what we're doing, is we're generating these polynomials that near the center, at the center, closely approximate our function in the sense that they have the same value, the same derivative, the same second derivative, and so on. Cool. Let's look at an example. Let's find this is what motivated our whole work in chapter 11. Find the 5th degree Maclaurin, that is Taylor centered at 0, polynomial for sine x. Use it to estimate the sine of 1. Okay, well, we know that the Maclaurin series for the sine of x I'm not going to recapitulate it here. We've worked it out. The Maclaurin series for the sine of x is the sum 0 to infinity, -1 to the n. It's the odd powers only, x to the 2n plus 1 divided by the corresponding factorials. Yeah, and if you want the fifth degree Taylor polynomial of that, well, you just have to start taking terms until you get an exponent that's a 5. All right, so the fifth degree Taylor polynomial, if you let n equal 0 up there in this expression, by this expression I mean this thing. Stop the video and go slower if you need to, but if n is equal to 0, that term is just going to be x. Yeah, and then when you click n up equal to 1, you're going to pick up a minus sign from the -1 to the 1, and the power would be x cubed. The factorial matches it. I'm going to keep going because the degree is not 5 yet, but in the very next term, click up n to be 2. 2 times 2 plus 1 is 5. So you divide that by 5 factorial. There's your degree. That's it. That's your degree 5 Taylor Maclaurin polynomial for sine of x. All right. And then what do I mean? Use it to estimate the sine of 1. This is probably, or some more terms of it, this is how your calculator calculates this thing. The sine of 1 radian, well, it should be pretty close to this Taylor polynomial's value at 1. I am not saying anything about error here, error. It's a little bit irresponsible of me. I'll say something towards the end, but for right now, I'm just kind of playing fast and loose. And you can check that this thing, well, T5 of 1 is exactly equal to 1 minus 1 over 3 factorial. 3 factorial, I'll remind you, is 6. Plus 1 over 5 factorial. 5 factorial, check me, is 120. So 1 minus a sixth plus 1 over 120. You can check this. I did the arithmetic earlier, so I don't have to go slow in the video, but I think that's the fraction 1 over 1 over 120, 101 over 120. So it's like our Redwood Highway divided by 120. And if you get a decimal for that, that's 0.841667 on my calculator to 6 decimal places. All right, so that's my estimate for the sine of 1, 0.841667. And I can estimate that by being able to do arithmetic. Yeah, that's why I like Taylor series. I can answer questions about transcendental functions like the sine in terms of an algebraic function like T5. Cool. Just FYI, you can check on your calculator. When I checked my calculator, the sine of 1 radian, plugging in my calculator said 0.841471. That was the display. So our estimate is accurate to, well, it looks like to 1,000th, 3 decimal place. 3 decimal place accuracy using that 5th degree Taylor polynomial. Sweet. Let's do another example. Let's use a Maclaurin series for sine of x to calculate this limit. The limit as x goes to 0 of that expression, sine x minus x plus 1/6 x cubed over x to the 5th. All right. So what do you mean use a Maclaurin series for this? Well, let me write it out. The sine, I'm going to write it just in longhand this time. The Maclaurin series for sine, we just had it above. It starts off x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Yeah. So if we took sine of x minus x plus 1/6 x cubed, well, sine of x minus x is going to cancel that guy. And since 3 factorial is 6, when we add 1/6 x cubed, we're going to cancel that guy. So when you subtract and add those terms, what you'd be left with is your x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So the expression that we're supposed to take the limit of, sine of x minus x plus 1/6 x cubed all over x to the 5th, we could just divide this polynomial side by x to the 5th. And so, well, we're going to get 1 over 5 factorial minus x to the, what, 2 over 7 factorial. You want me to write one more term? This guy up here would have been plus x to the 9th over 9 factorial. So we'd get x to the 7th over 9 factorial. But the whole point is that after this first term, everybody has an x in it. The only term that doesn't have an x in it is the first term. So if we're going to let x go to 0, I'm going to be a little fast and loose on my notation here and just write this goes to, as x goes to 0. Well, all these terms with x's in it are going to vanish. So we're going to get 1 over 5 factorial, or 1 over 120. So what's the point in doing this? Again, I'm just trying to show you how you can use a series to manipulate functions. In this case, I wasn't even using a Taylor polynomial. I was using the whole series, but plugging in 0 was simple because it killed lots of the terms. Nice. Okay. How about, so maybe you're impressed, maybe you're not. Let's look at this example. This is actually a relevant example in mathematics. This function that I've chosen here, e to the minus x squared, not exactly like this. There's some parameters that you have to put in to make it relevant to context, but it's important in probability and statistics. It's related to a certain distribution function called the Gaussian distribution or the normal distribution. And lots of different data sets are sort of arranged this way. Maybe you've heard people talk about the so-called bell curve. So the bell curve is the way data that's normally distributed sort of falls out. The average value of the data is represented here in the middle of the picture. It's the mean. And then the data is spread out equally on both sides of the mean in a certain way. So if you're interested in that kind of stuff, if you take like our Stat 108 or Stat 109 course, those are introductory statistics courses, and you can learn about how this function is used in statistical inference and probability. Here, I'm not going to get into the details, but I'm just going to tell you that questions about statistics and probability can get translated into questions about area below this curve. So again, I'm fudging a little bit here with some constants, but in some sense, the area below this curve represents the probability of a variable taking on a certain value. So modulo some parameters, this blue shaded area in your picture would represent the probability of kind of randomly picking something from this distribution and having it be between 0 and 1. All right, so all of that I'm just trying to kind of motivate your interest in this thing. You can forget about it because I can just ask a mathematical question. Well, what is the area of that curve, of that region? I'd like to know the exact area below the curve e to the minus x squared for x between 0 and 1. And well, I mean, I can write down an expression that answers that question. It's this integral. You want to know the exact area under a curve over an interval a to b, integrate the function from a to b. But the trouble is that our function, this very important function in statistics, this Gaussian function, it doesn't have an elementary antiderivative. Yeah, so what do I mean by that? I mean, I don't know a way of writing down some function that I can then plug 1 and 0 in to get this answer. I'm not just saying that I don't know an antiderivative for it. It can be proved. It's beyond the scope of our course here, but you can prove it doesn't have one. You can't write a function down in terms of the algebraic, trigonometric, logarithmic functions that we use whose derivative is e to the minus x squared. It doesn't have an elementary antiderivative. So the fundamental theorem of calculus is sort of worthless for computing this, yeah? But it's not worthless if we just wanted to approximate the answer. Well, an idea is, let's use a Taylor polynomial. Right? If I replaced e to the minus x squared with some polynomial, well, I can integrate any polynomial in the universe. So can you. Polynomials are the first functions that you ever learned how to integrate, right? So that's the idea. Let's use a Taylor polynomial. We can write it down, We know, I think, I'm sorry about that. I'm not going to write this in summation form because I'm just interested in a polynomial. The Taylor series for e to the x, not e to the minus x squared, but e to the x is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on, yeah? So the Taylor series for e to the minus x squared, I think we did this in the previous section 11.10 part 2 video. But what do? I'm just going to replace all those x's with minus x squareds. I just think of these x's as placeholders. Yeah, if I put something else in for that placeholder, then I get a series for it. So what am I going to put in for the placeholder? I'm going to put in minus x squared. The radius of convergence for this series is infinity, and replacing this, the resulting series will still have radius of convergence infinity. So if we do this, we would get like 1, and then replacing that with minus x squared, I'd get minus x squared. Replacing that one, the minus signs would wash out. X squared squared is x to the 4th. Then I'd get minus x to the 6th. Over 3 factorial, right? I'm doubling all the exponents, plus x to the 8th over 4 factorial, and so on. So we'll use a Taylor polynomial. What degree? I don't know. Maybe we'll use this constant polynomial. Maybe I should start writing them, although it'll get kind of messy. If I'm going to use this guy, I would call that T1. The first 2 terms, well, that's T2. Or sorry, T0 is the first one, 0 degree. If we use the first 3 terms, T3, and so on. Yeah. So the question is, well, how big of a polynomial to use? How big of a polynomial to use? How do I know how many terms if I want to accurately calculate this integral? So again, we're not, I mean, you can mathematically answer these questions. So people can say very sharp results about the error you get when you use a given Taylor polynomial. And in fact, if we had another week of class and another week of energy, I could even show you that you can pre-specify the error. So if your client wanted you to estimate this area to within a millionth, okay, we could calculate how big of a polynomial you need to make it a millionth, the error smaller than a millionth. But I'm going to relax here and do something just a little bit more modest. So I'm going to switch my screen. I've got a Desmos window. And in your activity for this section, I'm asking you to do something similar. So let me find my Desmos window here and share it with you. And I'm assuming that you can see it now. And what have I got drawn in this window? I've got my exponential function, e to the minus x squared. You can see it there drawn in red. And then I've got this Taylor series that we just worked out for it cooked up. Minus 1 to the n, x to the 2n over n factorial. And my usual picture, I've got a slider. What you're looking at right now is T0. That blue line is the constant function 1. That's the 0th degree Taylor polynomial. Between x equals 0 and x equals 1, I would say that it's approximating that red curve pretty poorly. So let's start looking at what happens when we increase it. So there's the degree 2 Taylor polynomial. It's 1 minus x squared. It's a better approximation. There's degree 4. There's degree 8. That looks pretty good. Or sorry, degree 6. It's always 2 times this number n. The degree 6 one looks pretty good. There's degree 8. So I'm satisfied with this because I'm trying to estimate the area between 0 and 1, right, under that curve. So if we used the degree 8 Taylor polynomial, this is not a super mathematically sharp thing, but I think you agree with me looking at this picture, that answer is going to be pretty darn accurate. It's going to be pretty darn accurate if we just integrated this degree 8 Taylor polynomial. So let's switch back to the whiteboard. So when you're doing your activity, when the directions say, use Desmos to decide the order, the degree of the Taylor polynomial you should use to make your estimate, this is what I want you to do. I want you to get on Desmos and look at more and more terms of your Taylor series until it matches the graph well enough on the interval you're talking about that it looks like it'll make a good estimate. Okay, so let's switch back. finding this whiteboard. Should pop back up here in just a minute. There we go. So I got to get some room to work. I haven't left myself a lot of room to work here, so I'm going to ditch some of this stuff. So you guys are with me insofar as you know that I want to calculate that integral up there. And we just said that if we use this degree 8 Taylor polynomial based on the Desmos equation, it looks like it's going to do pretty well. So what am I going to write? That this area that I want, it's pretty close to the integral from 0 to 1 of this degree 8 Taylor polynomial. So that's what we're going to compute. All right, it's not going to give us an exact answer. It's going to give us an approximate answer. And why is that easy to compute? Well, that's a polynomial. So without trying to do a bunch of arithmetic here, if I just start term by term anti-differentiating that function, well, it's x minus 1/3 x cubed. I'm not going to try to simplify this at all as I go. I'm just going to write 1/5 1 over 2 factorial x to the 5th minus 1/7 1 over 3 factorial x to the 7th. Do you see what I'm doing? I'm just integrating a polynomial. That's why I like to know Taylor series, because anything I need to do, I just need to be able to do it to a polynomial. So I'm going to take that big long expression and plug in 1. Okay, I'm willing to do it. It's 1 minus 1/3 plus, what's that going to be? That's 1/10. 5 times 2 factorial. I'm probably not going to be able to do this. 7 times 6 is 42. I can handle that one. Can you handle 9 times 24? That's 240. That's 216. Check me on that, but I think 9 times 4 factorial is 216. Minus plugging in 0. The lower limit gives all 0. All right. And you can check. I hope you'll pause the video and get out a calculator, check my math, but I think that this number comes out to 5651 over 7560, or that's approximately 0.747487. So if you wanted me to say approximately what the area under that curve is from 0 to 1, I'm going to say it's about that. It's a little less than 3/4. All right, based on the Desmos graph, I have a feeling that's a pretty accurate estimate. Can I measure the error? Yes, but not with what I've told you guys right now. So I won't hold you guys responsible, but I do want you to know as science students and math students that this is a known problem, that we could bound the error. We could say something about how much of an error we made in this calculation. So maybe next week, if you're interested in that kind of thing, maybe as a scientist, an engineer, a geologist, or something like that, if you want to talk about the error in Taylor approximations, that could be a completely appropriate topic for us to talk about while some of us are catching up or just coming back. All right, so this video is getting a little long. I do want to say something about error. Okay, so here's sort of the result. It's called Taylor's inequality. There are many results about errors in using Taylor's polynomials, but here's one of them. That the author here is denoting the remainder. So the remainder, R of x, is the difference between your function value and the nth Taylor polynomial. So maybe I could write that somewhere, that his Rn of x is the difference of f of x and the nth Taylor polynomial at x. So its absolute value is your error. The absolute value is the error, because you don't care usually if the error is high or low. So it's the absolute value of this difference is what I'm calling the error in a Taylor's estimate for f of x. All right, and here's what the theorem says. The theorem says that if you can find a number m that you can guarantee to be bigger than the nth plus first derivative, the next derivative that the first one you didn't use in your nth degree Taylor polynomial. If that m bounds that nth plus first derivative on an interval around the center, an interval of radius d around the center, then the error is no more than this fraction. All right, and that's valid on that same interval. So it gives you a way of producing a number. That number is right here, that is guaranteed to be bigger than or equal to your error. So some people usually say that it's a bound on the error. So let's end this video by kind of returning to our first example where we estimated the sine function at x equals 1. I did it with, if you recall, a 5th degree Taylor polynomial. Okay, so we used T5 of 1 to do that. Okay, well, if the function f of x is the sine function, its derivatives are either plus minus sine or plus minus cosine. So we can take that number m to be 1. Yeah, plus minus sine, plus minus cosine, they're less than or equal to 1 on every interval. So I'll just take m to be a 1. The nth plus first derivative of the sine is less than or equal to 1. So that's my m in the notation up there. So let's just try to use the theorem. It says the error on a 5th degree polynomial, so R5 at 1, so capital M is a 1, n is 1, so n plus 1 is 6. That's where the 6 factorial came from. And then we're choosing x to be 1, and our center was 0. So I'm plugging in 1 minus 0 to the 6th, and 1 minus 0 to the 6th is 1. So I end up getting 1 over 6 factorial as a bound on my error. And you can check on a calculator that 1 over 6 factorial is approximately that number, 0.00138889, right? So what is that? That's a bound. If I use the nth degree or 5th degree Taylor polynomial to approximate the sine, my answer is off by no more than this. My answer will be off by no more than 1,000th. Okay, so that's just a little taste of what people can say about these errors. Okay, I'm going to stop this to keep this video short. This, the last video actually of our 2020 online semester. I hope these things have been useful for you. I tried my best to try to make something that could stand in for us being able to be in the same place at the same time. And well, maybe I'll see you in a Zoom class next week. And I'll write an announcement on the Canvas page kind of outlining what my expectations are for week 15 in this class, so everybody's on the same page. Okay, thanks.